All right, let's get started. So now that we understand how the heart works, we're going to continue with the cardiovascular system. And we've already covered this, sort of how the heart is hooked up to the lungs and the rest of the body. And so what we're going to do is march through this circuit as if you're a parcel of blood. And we're going to consider two central variables in the cardiovascular system. These are two properties that are really important to how it works, its performance, and how it performs under healthy versus unhealthy conditions. So before we get there, let's march through the circuit. So we'll start with the left heart. The left heart, okay, so that's this side. So from the left heart, blood leaving the left heart goes to the rest of the body. We call that the systemic circulatory system, starting with the arteries. Then, of course, it branches down to the smaller vessels, eventually getting to the level of capillaries, where we have exchange with the body. Now, we're going to first, the exchange organ that we first talk about are the lungs. Okay, so when we're done the circulatory system, we'll talk about the lungs. So let's just think about circulation in the context of gas exchange. So again, the left heart is going to have the oxygenated blood. By the time the blood gets down to the level of capillaries, then it's going to be able to offload oxygen and take on CO2. Then the circulatory system branches into larger vessels. Those are the veins. Eventually, they're collected up in the vena cava, which returns all the blood into the right heart, where it is then passed on to another set of branches that eventually get to the capillaries in the lungs. Okay, so the two variables that we're going to think about are velocity and pressure. So there's two measures of velocity that are discussed when people are talking about the cardiovascular system. The first one is what we're looking at here, which is the linear velocity. So if you were to track a red blood cell as it's moving down a vessel, then you would be measuring this flow velocity or flow speed. The term flow rate, again, it's another confusing convention in physiology. Flow rate is a measure of volumetric flow. So the way you can tell the difference, if you don't remember the difference between speed and rate, because usually rate is a synonym of speed, but in this case, they actually refer to different things. The way you can tell the difference is you look at the units. So here we see centimeters per second. So flow velocity or flow speed should always be shown in centimeters per second because it's the linear distance traversed per time. Whereas flow rate is what you measure when you're talking about the stroke volume over the course of a beat. It's how much liters per second or other metrics of volume per second. That's the flow rate. Okay, so just to be clear, here we're talking about flow velocity. And this graph is a little weird because we're going to consider, well, it gets weird when we talk about pressure. Here it's not so bad, but what we're looking at is in these different regions what the average flow velocity would look like. And as you might expect, as blood passes through the left ventricle, it's in the left heart, it has a pretty high velocity, and then it slows down at the capillaries. First, the systemic capillaries, and then as the blood is collected up into the larger vessels, the veins, eventually the vena cava, and enters into the right heart, we can see that it accelerates. It moves faster in those regions, but then as we have branching again, there is a drop in velocity. So this is a very physiologically convenient feature because at the sites of exchange, that is the systemic capillaries and then the pulmonary capillaries, you want the blood to flow slowly. because it gives more opportunity for exchange, so gas exchange, for example. And so you want the resident time to be longer, and if you have a capillary of finite length, then that's achieved by having a slower velocity. So that's a good thing, but just because it's good doesn't explain why this occurs. So that brings us to our first question, which is what creates these differences in flow velocity? So we're going to consider simple hydrodynamics to explain first this, and then we're going to consider pressure in a similar way. All right, so what creates differences in flow velocity? Let's start with just a single vessel. And it's a cylindrical vessel, and just imagine that we're going to push some blood through this vessel. And so that blood is going to adopt the shape of that container. It's going to be cylindrical. And if we push a volume in one end of this vessel, we'll call that V in, and it's filled with blood, then as we push that volume in, we're going to have the same volume get pushed out the other end. This is simple sort of conservation of mass thinking, that as long as this liquid can't be compressed, and under physiological conditions, blood or any liquid in your body cannot be compressed. Blood is essentially incompressible, and you have to dive down in the Marianas Trench to see any minute change in volume as a function of pressure, and our bodies just aren't capable of those kinds of pressures. So the bottom line is that as you push a volume in, you get the same volume out the other end. So if you do this and for some period of time, then you can quantify this in terms of a flow rate. So that's, again, what we mean by flow rate is the volume per unit time. So that's the flow rate in, and then we have that being equal to the flow rate out. Since these two volumes are the same and it's traversing the same periods of time, it follows that the flow rate into the system is equal to the flow rate out of the system. This is known as the law of continuity. Okay, so that seems pretty straightforward, right? That makes sense. But it starts to get a little bit less intuitive when you parse the geometry. And so the volume you can think of as being the cross-sectional area times the distance traversed by one edge of the volume. So what I mean by that is this delta x here that the trailing edge of our volume passes through. And so that allows us to restate our volume in as the product of the cross-sectional area and the distance traversed by that trailing edge. And so we can restate the input side of things like this. The area doesn't change over time, but that edge, the trailing edge, does. So the flow rate in can be restated as the product of the cross-sectional area on the input side times the change in x over the change in t, otherwise known as the speed. So flow speeds are conventionally designated with a restricted u. And so you can say that since you have the same flow rate on the output end as the input end, then we can restate the same equation, and then we can use the letter u down below. So we're just, again, the principle holds. It's just conservation of mass, known as the law of continuity because we're talking about a fluid. We're just using a little bit of geometry to restate the same principle in a different way. But when you look at it this way, it really puts an emphasis on that cross-sectional area. And there are some important interpretations from this pretty simple relationship. First of all, an increase in area, that is, as you go down the length of a vessel, must have a proportionate decrease in speed, right? We're talking about the input-output end of things, but it's arbitrary where in the circuit you are considering. You could be considering the product of area and speed in the middle of that vessel. And so it holds that it's not just the input and output, but anywhere along the length of your vessel, this product should hold. So if suddenly the area goes up, if the product's going to stay the same, then the other number has to go down. That is, the speed has to decrease. Now, the law of continuity is also known as the thumb over the garden hose effect. So if you're watering your lawn and you stick your thumb over the opening to the garden hose, you're decreasing the cross-sectional area, and that causes an immediate increase in the speed of water as it flows out the hose. Okay, that product stays constant. So let's consider what that looks like geometrically. So just imagine, again, we're pushing this volume in, but we have a vessel that increases in its area. And so what you can see is on the output end of things, it's the same volume, but since it has to conform to the cross-section of the output end, you can see how the delta x over this period of time is going to be less on the output end than it is on the input end. And so just to drive it home, we can animate that. Again, these volumes are equivalent, but you get less distance traversed per unit time. In other words, less speed on the output end than on the input end because the cross-sectional area of the output is higher. Yeah, question?
This is due to the shape, right?
It's due to the cross-sectional area.
I don't know, but like, is it also due to the shape of the entire thing? Because when you go in, you have a smaller cross-sectional area as opposed to when you go out, you have a larger cross-sectional area?
That's right. So it's all due to area. So if it's the same volume and I'm changing the area, then there's only one linear dimension left, and that's the one that moves down the length of the vessel.
Thank you.
Any other questions? Yeah.
What would you do if you had like more than two different areas? Like, say it's like thin and then widens and then thins again?
Oh, okay. Yeah, so the question is what would happen if you had more than one area? So let's just say you were going along a vessel, and this example is that it starts off thin, it increases the diameter, and then it decreases in diameter. So all along the way, the product of cross-sectional area and speed holds. So as it increases in diameter, it's going to slow down, just like we see here. And then if it would then decrease in diameter, it would speed up. So what you want to consider is just, this product always has to be a constant. That's what the law of continuity says. And so if one number goes up, the other has to go down, if this is true. And so really, it's area that's driving this change in speed. You don't have any accelerations in the speed otherwise if you have this continuous circuit. And so what we're doing is that we're essentially modeling the circulatory system as the heart provides some flow rate, some volume per unit time. That's its job. It's delivering a flow rate. And then as you go through the circulatory system, the changes in speed are dominated by changes in cross-sectional area. So that brings us to the cooker question, which is just posing the question that we laid out with these possible answers. So the question was, what creates these differences in flow velocity that we see in this graph? A, differences in systolic pressure. B, differences in hydrostatic pressure. C, differences in temperature. D is differences in cross-sectional area. And E is none of the above. Okay, we're doing well on this one, so give me your final answer. Final answer. Okay. Yeah, so I pretty much just told you the answer, which is D. Changes the cross-sectional area. So let's look at that. So, okay, this is the pattern we laid out at the beginning. We see that there are these changes in speed. We know that that's a good thing. What creates the changes in speed? Well, It's because of the law of continuity that the changes in speed are driven by differences in cross-sectional area. So you might at first be perplexed by this. How can it be that we have a large cross-sectional area in the capillaries and a much smaller cross-sectional area in the left heart? And the answer to that question is that you need to consider the total cross-sectional area. So all of the vessels that run in parallel to each other. And so in the case of the capillaries, you take the cross-sectional area of individual capillaries, which is quite small, but if you then multiply by all of the capillaries, it is quite large. Okay, it's all of the cross-section in parallel. And it is just because of this geometric principle, that is having a very large number of capillaries creating a large cross-sectional area, that causes the blood to slow down. Okay, because at the level of the capillaries, the flow rate, that is liters per unit time, is the same as the flow rate in the aorta, where the blood goes whizzing by at high speed. So just because you're creating a very large cross-section, they slow down, that allows for exchange, and then as the blood gets collected up again in the veins, where you have a reduction in the total cross-sectional area, that causes the blood to speed up. So it's not because, at first you might think, oh, this should be driven by pressures. When things speed up, they're more pressurized or something like that. That's not at all what's going on here. There's no pump in the veins that's causing this acceleration in the blood. Instead, it's just because they're in a small cross-section. It's the garden hose effect. Please, no cell phones. Okay, and again, as the blood moves into the capillaries, large number of capillaries creating a large cross-sectional area, which slows the blood down, which allows for gas exchange to occur. And when you consider differences between the left and the right heart, and there actually are differences, for example, there's a subtle difference in the speed, you might think, oh, well, that's because the left heart is thicker in its musculature and generating higher pressures. And that is true, it does generate higher pressures, but the reason why it generates, wait, do I have this wrong? No, I actually have it wrong. Okay, so it's even less intuitive. So despite the fact that it generates those high pressures, you actually have a slower blood flow in the left heart, in the left ventricle, than you do in the right ventricle because of a difference in cross-sectional area. So there's a smaller cross-sectional area in the left heart than in the right heart. Okay, so that's the answer to flow velocity. If I pose a question to you on a test about flow velocity, the answer is probably going to come from a consideration of the law of continuity. All right, I've said nothing about pressure yet. Yeah, question?
You just said something about pressure for the left ventricle right now.
Well, yeah, and because I was illustrating how it didn't have anything to do with this difference in velocity. So I did use the word pressure, but it wasn't in the explanation of the difference in velocity. Yeah, question?
Just to clarify something, so you just mentioned that even though the thickness is like higher for the left ventricle, for the left side, the cross-sectional area is smaller, so the speed is.
Yeah, sorry, just to be clear, yeah. So the walls of the left heart are thicker. The musculature in the left heart is thicker. And if you remember back to when we talked about muscles, if you have a thicker muscle, you can generate a higher force. So the left ventricle generates higher force, and as a consequence, it's capable of generating higher pressures. But what this graph shows is the cross-sectional area, and this cross-section on the graph is the cross-section of the blood. It's of the space inside of the ventricle. So that cross-section is actually smaller, maybe because its walls are thicker, than the right heart. So the right heart in the cross-section of this chamber sort of providing a blood vessel is smaller in the left ventricle than the right ventricle. As a consequence, the blood flow is higher than in the right ventricle. So I did actually say it backwards because you have a higher velocity because of the smaller cross section, not because of pressure. Okay, now what about pressure? So this graph is the one that's a little bit weird because I'm going to show you some oscillations in pressure that occur as a function of time for these different regions. So the x-axis is both a sort of what happens as a function of position, but within each of those regions, we're going to consider how things look as a function of time. So for example, here we have in the left heart those big oscillations in pressure that we talked about before when we looked at the Wiggers diagram, and we went through all the details in the last lecture about valves and blood flow in certain directions and everything. So that's what it looks like. You get these very large oscillations in pressure. Now, as the blood moves through the aorta into the major arteries, we see this strange phenomenon of the high pressures during systole, known as the systolic pressure, mirroring what's in the left ventricle. But during diastole, that is when the left ventricle relaxes, we can see that the major arteries retain an elevated pressure. Okay? So that's what's weird about it, is it has this ability to maintain the higher pressure. So we'll talk about that in a little bit. So these are what are measured when you get your blood pressure read when you go to the doctor's office. So your arm is pretty close to your aorta, and so it provides, once you calibrate this device, an ability to monitor essentially the peak pressures that are generated in the left ventricle, and then the pressures in your aorta when the left ventricle is relaxed. If you could then move with the blood into the smaller vessels and eventually into the capillaries, you would find the pressure drops precipitously. Again, that's a good thing because the walls of the capillaries are very thin to allow for exchange. That's a good thing in terms of Fick's law, but it's bad in terms of structural integrity. Those vessels are very delicate. It's very easy to burst burst the capillaries. And so if you had those really high systolic pressures like the aorta experiences, they would just blow out the capillaries. So it's a nice feature that the pressure drops just like the flow speed. And as the blood is collected back up into the veins, we don't see a re-elevation of pressure like we saw for velocity. Instead, it stays at this rather pathetic low level until it enters into the right heart. And then we see that the muscular contractions of the right heart inject some pressure again, which then also gets sort of sapped out of the blood as it moves into, that's the pulmonary capillaries there. So when blood is pushed through capillaries, small vessels, the pressure drops. And it's only in the heart that there is the introduction of elevated pressures. All right, so the question now is, what creates this pattern of pressure, or what creates these differences in pressure? Okay, so now our consideration of fluid dynamics is not going to be just in terms of the geometry of the vessels, but we have to think a little bit more mechanically. And for that consideration, we're going to go down to the level of the capillaries because it makes sense to us that pressure should go up in the heart, right? Because the heart is muscular, it generates tension, it then exerts that force on the blood contained within the vessel or within the chambers. But what about this dropping of pressure? What drives that? So let's consider, again, it's a cylindrical vessel, but it's at the scale of a capillary, a small vessel. And if you were to tag a cylinder of blood and watch it as it enters into a capillary, then you would see that it adopts something that looks like this. It would be a little less, it would be smoother and not quite so pixelated. But the reason why I drew it this way is to explain in simple terms the mechanical interactions between little volumes of blood. So what's happening here is that this parcel of blood that touches the wall of the capillary, its bottommost layer adheres perfectly. Those molecules get stuck to the wall of the capillary, because blood, like all fluids, has viscosity. That's essentially the stickiness of the blood. And since blood is sticky, as you attempt to move a fluid such as blood over a surface, then there'll be a monolayer of molecules of that fluid that just stick perfectly to that surface. Now, air is also a fluid. It operates by the same principles. It has a different viscosity, but because air behaves in a similar way, when you turn the blades of a fan on, or when you turn a fan on, the blades, as they move through the air, fail to remove dust that accumulates on those blades. And you might wonder, like, well, why can there be dust when the fan is moving a lot of the time? Why doesn't the dust just fly off? Well, what happens is that there's a monolayer of air that sticks to the fan blades. And so that monolayer moves with the fan blades. And so from the perspective of a dust particle, there is no relative motion because it's in that little stuck layer. So on the surface of this capillary, if you had a little bit of dust there would be no relative motion. It would, the velocity of that monolayer would be 0, and the wall of the capillary is zero as well. So this in fluid dynamics is known as the no-slip condition. There is no slipping between a monolayer of the fluid and a surface. So then what happens is you have a layer that's not going anywhere that is then adjacent to another layer that is being propelled down the capillary. And the viscosity between those two layers will effectively slow down the next layer so it won't displace by so much as the layer of fluid that's above it. And so then what you have is viscous connections between these layers of fluid serving to slow them all down, but they're at least inhibited in the center of the vessel. And so that's where you get the most displacement right there. Okay, this one travels the furthest in this period of time because it is just the furthest from the walls that have this monolayer that's attached to them. And if you measure this in terms of velocity, then you get these very smooth gradients that look like this, where the length of those vectors encodes a velocity, and you see the velocity is highest in the center of a vessel and lowest towards the walls. So this phenomenon of a flow gradient, it's a spatial gradient in flow, is created by the viscosity of the blood. And so it would change its shape if the blood changed its viscosity. And so its viscosity, which is shown here as eta, provides a source of resistance. It's resisting that motion of blood down the vessel. And you can quantify that resistance using a simple principle, sort of first principles consideration. This has been modeled for a viscous fluid being pushed through a cylindrical channel. And the resistance is proportional to viscosity. So you make it more viscous, more sort of honey-like, then there's going to be more resistance. That makes sense. It's also proportional to the distance that the fluid has to move along the vessel. And we can call that L. And it's inversely proportional to the radius to the 4th power. We see like nothing in physiology to the 4th power except for this one. So a very small change in radius has a huge effect on this uppercase R, the resistance. All right, so the radius of that vessel is really, really important. All right, there's a couple other constants in there so that we can change our proportional sign to an equal sign. And that very simple relationship known as Poussey's law shows us the relationship between a couple of geometric properties of a cylinder, its length and its radius, and the viscosity, and we can directly calculate how much resistance that vessel is going to provide. And what that shows us, just by looking at those terms, is that viscosity causes the radius to affect the resistance. All right, radius wouldn't matter if this fluid had no viscosity. It's because of the stickiness to the walls that radius matters. And we also, as a consequence of viscosity, get a loss of pressure. In fact, that's one way of defining viscosity, is that it is an energy loss. And that energy is dissipated in terms of heat. So as you take a viscous fluid, force it down a vessel, If you monitor pressure, you get a pressure drop, and that can be perfectly explained by a loss of energy via thermal dissipation. Any questions about Poussey's law? Yeah, question?
So what's L again?
L is the length of the vessel. Right? It's this distance here, from that edge to that edge. Any other questions? Okay, so this is, again, created by the stickiness or the viscosity of the fluid. So here's a clicker question. How does your body quickly vary the resistance along a vessel? A, by changing its radius, B, by changing its length, C, by changing the blood viscosity, D, altering blood volume, or E, changing temperature. All right, just started the software. Okay, give me your final answer. Okay. So the correct answer is A, change the radius. Most of you got the right answer. Note something here. So when we talked about continuity, what mattered was the total cross-sectional area of all capillaries. But if you're taking a bolus of liquid and you're forcing it through like a strainer or a bunch of very small vessels, then it's the radius of the individual vessel that matters. So this R, it doesn't really matter how many other vessels there may be. All that matters is the individual radius, right? Because we're modeling the resistance that they each provide, and if they all have that same radius, then they're all contributing with the same amount of resistance. So Poussey's law just really emphasizes the importance of radius on peripheral resistance. This phenomenon helps explain the ability of the central nervous system to control blood flow. And the way that it does that is through smooth muscles that are wrapped around the vessels that are next smallest to the capillaries. So what we have here are a bunch of capillaries. Just imagine that there's a bunch of oxygen-starved cells in these white spaces. And the blood is coming from the arterial side right here. And we can see that this vessel here is wrapped in smooth muscle. That's what that layer is showing. And then it moves down to the level of capillaries. And you can see those thin walls of the capillaries. Those epithelial cells are referred to as endothelium of the capillary. And you can see that there's a single endothelial lining of the capillaries, which makes them really delicate. But just upstream of those capillaries, you have an endothelial lining and a thin layer of the smooth muscle. So what arterioles provide is, since they're small in cross-section, they have a small radius, is they provide a lot of resistance, almost as much as the capillaries themselves. But it's because they're wrapped in smooth muscle, that provides your body with the opportunity to vary the radius. The capillaries are basically fixed in their radius, so we can't really control something that's fixed. But because of those smooth muscles, your autonomic nervous system can vary the radius of the arterioles. So I'll get back to that point in a minute. All right, so first of all, Poussey's law helps us understand why there were these big drops in pressure as blood was forced through the capillaries. It's just because they're really small in radius and blood is viscous. So that's why we get that big drop there, and again, the other drop that we see in the pulmonary capillaries. Okay, so again, pressure oscillations are created by the muscular contractions in the heart, and we get these drops in pressure that are created by high resistance and viscous dissipation. And we can predict those using Poussey's law. So the only aspect of this graph that we haven't explained so far is what goes on in those major arteries where we have this elevated pressure during diastole. So when the heart's relaxing, the aorta is still pressurized. So how can that be? Any hypotheses? No?
Can you give us?
Well, I could tell you the answer, but that's not really a hypothesis. Yeah.
Just to clarify.
Yeah.
So when you mean by time position, the x-axis, what do you mean by that again?
So the x-axis on this graph is pressure in these different regions that are shown up top, but they're also showing the temporal oscillations in pressure in those different regions.
Thank you.
And actually, I didn't really point it out before, but so you see those big oscillations in the left heart, and then when you get the systemic capillaries, this isn't just a poor drawing, which I'm perfectly capable of, but it's actually, you don't have those kind of oscillations in the capillaries. So that's another property of the viscosity of blood. So viscosity resists motion, and it effectively damps out those large oscillations that come from the heart, so that by the time you look at the capillaries, you don't get motion that's back and forth. It's pretty unidirectional and it's smooth. Yeah, question?
So you want us to hypothesize why the pressure is constant?
No. Why is the pressure elevated in the systemic arteries?
Oh, okay. So high amount of force, lots of contraction.
Well, so pressure suggests high force per unit area. That's what pressure is. So the question is, where does that pressure come from? Because it's not coming from the heart. The heart is relaxed, and it generates a very large drop in pressure. No, it's not the lungs. I'll just tell you the answer. Okay, so the answer comes from looking at the construction of those major vessels. So up top, we have an artery, and we can contrast it to the arterioles that I just told you about that have that smooth muscle lining. And if you dissect layers of the aorta, what you find is that there's a lot of extracellular tissue. Collagen is a major protein in these layers, and collagen is very springy. It's a very elastic layer. And so what the textbook shows here is the elastic tissue is a robust network of collagen outside of the cells. And what that means is that when the aorta gets pressurized, it functions like a water balloon with really rubbery, resilient walls. And so if you look down the length of one of these vessels, then it bounces back. And so during systole, you have an expansion maybe of its walls. And then during diastole, it's essentially remaining in tension, like a water balloon. As you inflate a water balloon, the internal pressure of the water in that balloon is generated by the tension in the walls of that balloon. And so it's because of this elasticity and this water balloon-like property that even during diastole, we have an elevated pressure. So the diastolic pressure is created by the elasticity of the arterial walls. So let's take that idea and plug it into our conceptual model for how the heart works. So we laid out that the left ventricle is sort of like this piston, and it has a semilunar valve that provide a way of isolating the pressure oscillations in that chamber from the major artery. That major artery first is the aorta, so we're going to draw the aorta as if it's a water balloon. And then on the downstream side of the aorta, you have a branching network to smaller vessels. So that's what we're going to show there. But ultimately, that's a bunch of capillaries. So as the left ventricle pumps blood and inflates the aorta, that expands the aorta. It's in tension at that point. And when the semilunar valve shown here is open, then the high pressure in the left ventricle is felt in the pressure of the aorta. Okay, that's the systolic pressure. We just saw the oscillations of systolic pressure in both the left ventricle and the aorta. Okay, and we'll just redraw that up top. So here we have the pressure in the left ventricle, big oscillation up and down, and we attain those high values in the aorta, but then we don't get the low values, so that we have a systolic pressure that's the same in both, that's being driven by the ventricle. The diastolic pressure, again, is being created by the elasticity in the aorta, and note that we can have different pressures during diastole because the semilunar valve is closed. Now, the aorta functioning like a water balloon means that blood spills out from the aorta and the other major vessels. And the rate at which it spills out and leaves this part of the circulatory system depends on peripheral resistance. Okay, now if we want to monitor pressure, it's quite often useful just to focus on a single value. And you could get that value by monitoring these oscillations in pressure over time. And if you take the mean value, it would be approximately close to that dotted line. Okay, so that dotted line is what's called the mean arterial pressure. It's just the mean as a function of time. And you can approximate that if you go to the doctor's office, they don't have this kind of temporal resolution and they don't calculate the mean. Instead, you can approximate that mean just by having measurements of the systolic and diastolic pressure. And that's done as a weighted average, where you take the diastolic pressure, you add 1/3 of the difference between systolic and diastolic, and that comes pretty close to where this dashed line is. Okay, so the reason why I mentioned that is that we want to later on pose questions about what affects pressure. And since we have systolic, diastolic, it's varying with time and everything, it just is a lot simpler if you focus on a single value, the mean arterial pressure. Okay, so how can we control this system? This is going to be more, this is going to be very important when we talk about cardiovascular control later on. And so I'm just sort of laying out all the parts, and we'll return to this conceptual model later. But in addition to having control over what the heart does, which is in turn inflating the major vessels, we also, because of having these arterioles that allow us to control peripheral resistance, allow us to influence the outflow from the major vessels. So when the arterioles contract and generate vasoconstriction, that greatly generates peripheral resistance, which in turn functions to keep the diastolic pressure elevated. So let's think about that for a second. So systolic pressure, it's being generated by the left ventricle, right? So if we look up top here, we're going to look at this trace of the pressure in the aorta, and I'm going to trace on top of it the systolic pressure. Okay, that's left ventricle generated. But now in this situation, we've added in green here vasoconstriction. Okay, so green and purple. So purple's, when you don't have vasoconstriction. And so when you do, shown in green, it looks exactly the same. That's because what's going on in the arterioles has nothing to do with the systolic pressure. Where the arterioles matter is what happens during the relaxation. You're inflating this water balloon, but it's the outflow of blood from the major vessels that the arterioles have an effect on. So it's during diastole that the vasoconstriction at the level of the arterioles influences the blood pressure. And because of that influence during diastole, when there's high peripheral resistance, and this is what we see up here, when there's high peripheral resistance, you get an elevation in the mean arterial pressure. Okay, does that make sense? This is what happens when, across the board, your body causes your arterioles to constrict. Okay, so we call that systemic vasoconstriction. And your autonomic nervous system has this ability to cause your blood vessels to constrict and prevent outflow of blood during diastole from the major vessels. And so that causes an elevation in blood pressure. Does that make sense? So we're integrating what the heart's capable of, where we can have changes in heart rate and stroke volume. We'll talk about the details of that later. And here we see how in the periphery, that is in the small arterioles in your systemic circulatory system, there's a level of control that is influencing the pressure in the major arteries. Question?
You mentioned how the arterioles affect the aorta. Aorta pressure, how?
So so imagine a water balloon. We're filling it up with water, or we're filling it up with blood if you want to be morbid. So you're filling it up with blood, and when it's the most full, the walls are in the most tension because they're very springy, and like a spring, you get the most tension when you pull it the furthest. And you can release that pressure by letting the blood spill out of the water balloon. If you sort of open up the opening to the water balloon, it will spill out. The walls will decrease in diameter, and the pressure will go down. So you can think of peripheral resistance as having control over the rate at which blood spills out of the major arteries. If there's high resistance, the arteries stay inflated during diastole and keep that pressure high. And you could measure that by the mean arterial pressure. It's going to have a relatively high mean arterial pressure when that peripheral resistance is high. You can also, the central nervous system also has the capacity to differentially generate peripheral resistance. So if you're being chased by a bear, it's a good idea to send blood to your muscles and not to your viscera, right? Because there's a lot of blood flow. No cell phones, please, people in the back. There's a lot of blood flow that goes to your viscera because when we're absorbing nutrients, blood flow is there to pick up those nutrients. So being chased by a bear, you want blood going to the muscles and not to your small intestine. And so that introduced the notion of local vasoconstriction. Not only do we systemically control the arterioles, but we might also pinch off the arterioles that are just in the viscera. And when you generate an elevated peripheral resistance in some vessels, then you're going to have higher resistance there and relatively low resistance in other vessels. And as a consequence, because of Poussey's law and this high effect of radius on resistance, there's going to be preferential blood flow to those relatively large diameter or large radius vessels. So what we're seeing here is that blood is being shunted towards the vessels with the lower resistance, which are also larger in diameter. Okay, so to summarize, we've got the left ventricle generating systolic pressure. We have peripheral resistance regulating the diastolic pressure and also allowing for shunting, that is differential blood flow to different organs. And the role of the aorta is key here because it's functioning as this water balloon that elevates the pressure during diastole. And question?
What shunting means?
Shunting means we're differentially pushing the blood towards some vessels and closing down other ones by enhancing the resistance in those ones that are not getting much blood flow. So a shunt is sort of pushing away from one region to another. So we'll pick this up next time. Thank you.